Hello and welcome all to the second part of the series where we are discussing Apache Hadoop ecosystem and what some of the important technologies within the Apache Hadoop ecosystem. So as we discussed in the first part of this discussion also, agenda is high level objective of the presentation. I talked about this in the first part. I'll just briefly touch again in this part also, and we'll be discussing some of the technologies which comes under the umbrella of Apache Hadoop for big data and analytics platforms. Okay, so in the first session, first part, we discussed Hadoop, HBase, Cassandra, and Hive. This part we will be discussing Kafka, Flume, Spark, Storm, and Scoop. Okay, so objective, as we discussed in the first part of uh, presentation series, that objective of this discussion is to give a high level overview of Hadoop ecosystem, so that architects and system designers who are from non-analytics background, who haven't handled any projects in big data and analytics domain, they can at least understand what are the offerings from Hadoop ecosystem, and what are the technologies which it offer, and what are the best use cases to use those technologies. Okay, and another important point is that intention of this discussion, this presentation series, is not to make you expert in any of the Apache Hadoop and related technologies, but just to give you idea about how those technologies can be used in different use cases, different requirements. So it will not make you expert in any of the technologies, or we are not going to compare offerings from some other vendors and other companies which are in kind of competition with Apache Hadoop. We are not going to compare different stacks here. So first part we discussed about Hadoop, HBase, Cassandra, Hive. This will start Apache Kafka. Okay, so Apache Kafka is basically a publish subscribe messaging system. Okay, so we all know different messaging systems like ActiveMQ, WebServeMQ, Sonic, and all those messaging systems. So Kafka is also a messaging system which is based on publish subscribe or pub sub model of messaging. It originated at LinkedIn. LinkedIn people, they wanted a messaging system to have a very fast, reliable, and which should be able to handle high throughput kind of system. So they designed Apache the Kafka, and later they gave it to Apache through open source and all those things. So motivation for LinkedIn team was that they needed a unified platform to handle all the real-time data feeds that a large company might have. Okay, so some of the requirements they wanted out of the messaging system was that it should be able to support high volume event feeds coming in real time. It should be able to handle backlogs from the offline system. So in most of the scenarios, you must have handled this requirement there, where one of the system would be sending huge backlog in periodic intervals or batch intervals instead of real time. So the new messaging system they wanted, they should be able to handle this requirement as well. Apart from the real time requirement, it should be able to handle the backlogs through offline, coming through offline systems. Again, another requirement was that it should be able to cater existing or traditional messaging use case as well. Plus fault tolerant and high availability should be built into the platform. So these were some of the requirements, and using these as uh, based on these requirements, they finally came up with Kafka, which is meeting all these requirements. We'll discuss briefly about Kafka architecture now. Okay, so at high level, in Kafka, we have producers which are generating messages, basically writing data to the Kafka brokers, and we have consumers which are reading data from those brokers. And all this is distributed. So we have producers and we have consumers as well as brokers. All those are distributed across very low end servers. You don't need high end servers like you know, which is the common thing across all Hadoop ecosystem. So we have producers, we have consumers, brokers, all distributed across simple servers. And the data is stored in topics, which are again partitioned and replicated across different machines. So if you look at at this diagram, so we have Kafka cluster, where you will go and configure brokers, and in those brokers you will have topics on different machines, partitioned across different machines, and replications etc. is built into the platform. You have different producers which are generating messages and putting onto the topics, Kafka topics, and consumers, they will go and read messages from the topics they are interested in. Okay, so all these will go and pull the required messages. So at high level architecture of Kafka continues. So we have producer. If a producer wants to publish a message to a given topic, they will simply append to the end or the tail of the queue, topic basically. Sorry. So producer always append to the tail. Okay. While consumer, if a consumer has to read a message from a topic, they have to specify one offset also, that the message which they want to read, say one consumer wants to read fifth message, another consumer wants to read second message, or whatever is the message, they need to specify offset also. So consumer use an offset pointer to track control their read progress and decide the pace of consumption. So depending upon the rate individual consumer are processing, one of the consumer group is basically a collection of consumers which are processing the message. So one consumer can be getting or reading fifth message, another one is still working on the second message. So it is the responsibility of individual consumer group to tell which particular message they want to consume. Okay. So key design elements in Kafka are end-to-end batch compression. Okay, so you have huge batch of messages to be transported. Compression can save you, all those bandwidths and network latencies because of huge data size because of the compression. Asynchronous send is there. Producer simply tell that this message needs to be pushed, and that's it. Producer can continue working with another functionality or another logic. It can execute that. It will automatically get the acknowledgement once the message has been pushed onto the topic. It's a push from producer is pushing the message onto the queue, while consumer has to pull, specifying the offset and everything which we discussed previously. So some of the use cases where Kafka is used. So LinkedIn, they are using it for activity streams, operational metrics, etc. And if just to give you an idea of the size of Kafka in their ecosystem, it is running 400 nodes, 18,000 topics, and at peak they handled 3.2 million messages per second. This is to 2014, almost 2 years back now. Okay, Netflix is using it for real-time monitoring and event processing. Twitter is using it for their storm-based real-time data pipelines. And so there are different use cases, case studies also available on the net. You can have a look for detailed things. Almost all the scenarios Kafka is being used these days. Okay, so now we will go and discuss Apache Flume. Apache Flume is a distributed, reliable, and available system for efficiently collecting, aggregating, and moving large amount of log data from many different sources to a centralized data store. So you have a huge data, logs data. Basically, log data is a kind of misnomer. You can use it for wide variety of source data, not just the logs, but original purpose of designing Flume was to move the log from different sources, application logs, web servers logs, etc., to a centralized storage, basically SDFS based storage into Hadoop. But now you can use Apache Flume for not just logs but from other sources also to other not to other destinations or other sinks which are not just SDFS. But the primary objective of Apache Flume was to move different kind of logs into SDFS Hadoop systems. Okay. So use of Apache Flume is not only restricted to log data aggregations. Since data source is customizable, Flume can be used to transport massive quantities of event data, including but not limited to network traffic data, social media generated data, emails, and pretty much any data source basically. Because though originally it was intended to move only log data, but because of the programming model, you can configure, you can customize different sources, and you can basically work with any kind of data. So the flow of Apache Flume is basically you have a different data coming from different sources, which is called uh, payload. That data is in byte payload. So plus you can also specify different attributes, optional attributes, quality of services, and all those kind of things you can specify with that. So agent is nothing but a JVM process basically. Okay, so Flume agent is a JVM process that hosts the components through which events flow from an external source to the next destination. So data coming from different sources. Okay, it enters the Flume agent where the Flume source basically will parse that data, validate that data, and do the required processing and put it into a channel. Okay, channel is a kind of queue. You can understand, you can take it as a queue. It basically which is it's a nothing but it's a passive store. Okay, so after doing the required processing, source will push that message, if we can call it so, to the channel, and then sync will get that message or get that data from the channel and put it into the SDFS or wherever. So like sources, syncs are also configurable and customizable. You can very well use a sync to write to some other data source. Okay, right now we are showing it as SDFS, but you can write it to any kind of storage. Plus you not just you can always pass it to a next channel where another sync will consume it and do the necessary processing. So it's not just one source, one sync, and one channel. You can have combination of this in a given flow. Okay. So sync removes the event from the channel and puts it into the external repository like SDFS via Flume SDFS sync. If you have to put it onto SDFS, there are already pre-built Flume SDFS syncs available. If you have to put it to some custom source destination, you can also do that also. Kafka, we discussed a publish subscribe model. Flume is also kind of doing something like that get the message, put it into the channel, and again process it from via the sync and put it into the SDFS. But there are some differences also. Okay, so Flume's main use case is to ingest data into Hadoop. That was the primary use case for designing Flume. Okay, it is tightly integrated with Hadoop's monitoring systems and all those file systems, storage, etc. Flume design of sources, sinks, and channels mean that it can be used to move data between other systems flexibly. As I said in previous slide, that all these sources, sinks, and channels, they are customizable. It's not just any longer it's not any longer meant only for log movement to SDFS. You can use it for practically any purpose. But the important feature is its tight integration with Hadoop. Okay, so Flume is very tightly integrated with Hadoop. While on the other hand, Kafka is a standard distributed publish subscribe messaging system. It allows subscribers to read exactly the message they are interested in. Okay, so consumer will tell the offset pointer which message they want to read it, and making sure that distributed system is also scalable and reliable under many different conditions. So all the scalability and reliability, they are built into the Kafka system. Okay, it was not written to stream data specifically for Hadoop, and using it to read and write data to Hadoop is significantly more challenging than in it is Flume. Flume, because it was primarily intended to read and write into Hadoop, it is very easy in Flume. Kafka, it's a generic system, so you have to do your own things. Though there are built-in, connectors now available, but yeah, still it is much. If your requirement is simply read a log file or that kind of thing and push it into HDFS, Flume will make more sense. Okay, now next we are going to discuss Spark. So Spark is getting very popular these days. So uh, Spark is it's a open source, of course it's Apache, so it's a big data processing framework built around speed, ease of use, and for very advanced analytics also. Okay, so like MapReduce, which is a data processing framework, Spark is also a map data processing framework for big data analytics. Okay, but difference is that Hadoop's two-stage disk-based MapReduce program functionality or model, it's a disk-based model. MapReduce map operations will do the map functionality where and then it's a two-phase operation, right? We discussed in the first part, but almost all that functionality is disk based. Okay, get the data from HDFS, do the processing, and then write back the results to HDFS. Spark on the other hand is in memory processing, so it is much more faster than a standard MapReduce program. Some of the benchmarks which are there on Apache Spark site, it shows that for a given use case you can see up to 100 time performance gains for Spark as compared to MapReduce. Okay, resilient distributed dataset or RDD, it is the core component in Spark framework, core concept in Spark framework. So I think RDD as a table in the database. Okay, it can hold any type of data. So RDD is nothing but a kind of table in the memory for your data. Okay, Spark stores data in RDD on different partitions. Again, like most of the Hadoop technologies, Apache Hadoop technologies, Spark is it partitioning and those kind of things are built into the Spark function, Spark stack. So there are different features or different components in Spark. One is the data, which is actually nothing but the storage. It can be HDFS or it can be any other storage. Then there is a compute interface, which is you can use APIs in Java, Scala, Python, etc. And then there are management like Yarn and other cluster management, resource management tools. So these three are the main components of Spark. And Apache Spark core. This core is the foundation of overall Spark stack. Okay, so Spark core is the foundation of stack. It provides distributed task dispatching, scheduling, and basic IO functionality. So all the scheduling, job scheduling, task dispatching, etc. is handled by this core. The fundamental programming abstraction is called RDD or resilient distributed datasets, a logical collection of data partitioned across machines. Okay, so we discussed RDDs are partitioned. RDDs can be created by referencing datasets in external storage systems or by applying some cross-grained transformations, for example, map, reduce, join, filter, etc. on existing RDDs. Okay. So as we discussed, what this exactly means is RDD, you can think it as a table for the given data. Okay, so you can create RDDs by referencing some of the data sets which are lying in external storage, maybe say HDFS, or if you already have RDD in memory, you can apply some necessary logic. Say you want a subset out of that. Okay, you want to do some filtering on some parameter and create a separate RDD out of the big data sets. So that's how you can create RDDs in Spark. Okay, Spark SQL give you feature to expose all those data sets, and you can use it via JDBC API and allow running the SQL like queries on Spark data. Okay, so you can use Spark SQL for querying those RDDs using JDBC APIs and all those things. Spark streaming for real-time handling. if you have real time streams coming into the system, you can use Spark streaming. Machine, like if you have a requirement where you need to do some machine learning algorithms, for example clustering or classification, etc., you can use mlib library of Spark. And for any graph database or those kind of functionalities, you can use GraphX libraries. Okay. Some of the major use cases in which are where you can use Spark is iterative algorithms in machine learning, data mining, data processing. Spark is fully Apache Hive compatible data processing system that can run 100x faster Hive than Hive. We discussed in the first part that Hive internally launches MapReduce jobs, okay, which are disk based processing. Because Spark is in memory, so you can always create a Hive query and run it on top of a Spark system, so you will have better performance because Spark will give you in memory processing. And if you have a stream processing requirement, you can use Spark, for example log processing and fraud detection, etc. You can use that. Sensor data processing, where data is fetched and joined from multiple sources. In-memory dataset really helpful as they are easy and fast to process. Sensor data, you have different sensors and small devices, which is getting popular these days, Internet of Things kind of thing. So you can use Spark in that scenario also, where you need to process those high velocity data coming into the system. You can use Spark in also. Okay, so now we'll discuss Apache Storm. So Storm is a distributed real-time computation system for processing large volume of high-velocity data. So this line basically sums up, uh, everything about Storm. You need real-time handling of streams coming into the system at high velocity. You have to use Storm. Okay, it is one of the most popular and most powerful framework for handling real-time streams. It makes it easy to reliably process unbounded streams of data, doing for real-time processing, but Hadoop did for batch processing. Okay, so with Hadoop MapReduce, you it basically Hadoop simplified handling those huge amount of data because of MapReduce running into distributed clusters where small chunks are being processed at individual server. The same thing is Storm is doing for real-time streams. 5 characteristics that make Storm ideal for real-time data processing. Storm is very fast, scalable, fault tolerant, okay, reliable and easy to operate. So fast, scalable, we all understand, uh, fault tolerant, when workers die, Storm will automatically restart them. If a node dies, this worker will be restarted on another node. Because this is built into the Storm framework, Storm will automatically do all these things. Okay, Storm also guarantees that each unit of data, which is called tuple, is processed at least once or exactly once depending upon the configurations. Messages are only replayed when there are failures, otherwise it guarantees at least once or exactly once. Easy to operate, very easy to configure and handle operations of a Storm cluster. It's not a big operational entity. It's not a big problem to handle it operationally. So high level architecture of Storm, we have a master node or called Nimbus node, which is doing major things like upload computations for execution, launches workers across the cluster, distribute code across the cluster. So it will allocate, it will basically start that it will start different workers, see if they have completed, etc. And if some relocation allocation needs to happen, it will handle that also. It uses Zookeeper. Apache Zookeeper is a resource management and cluster, resource management framework from Apache. So it uses all these things for coordination. Typical use cases: supervisor nodes communicate with real-time stream processing, Zookeeper, start and stop workers according to signals, real-time analytics from social media analytics. For example, Twitter hashtag at supervisor, which tag is trending and all those things. It is Storm You can use Storm in those kind of scenarios. Fraud and threat detections and many more case studies are available on this link. You just have a look at this Apache Storm site and you will see how Storm is being used to handle all those real time scenarios across industries. Okay, so next is Apache Scoop. Scoop is basically, it's if you have a data in your data warehouse or RDBMS systems, etc., which you need to move to say HDFS, okay, or you have data analyzed data, aggregated data in HDFS, and you want to move it to some your own data warehouse for some reason, you can use Scoop for that. So Scoop is tool designed to transfer data between Hadoop and relational databases. You can use Scoop to import data from RDBMS such as MySQL or Oracle into HDFS and transform the data in the Hadoop MapReduce and then export back to RDBMS again. So you have data in your MySQL, say you move it to HDFS using Scoop, do all kind of processing using MapReduce or whatever processing framework you want to use, and send back the results to RDBMS for some reporting and all those things. Scoop automates most of this process, relying on the database to describe the schema for the data to be imported. Okay. Scoop uses MapReduce to import and export the data, which provides parallel operations as well as fault tolerance. So if you say this data from MySQL, this table needs to be moved. Okay, so internally Scoop will launch MapReduce operation so that in parallel all that data can be fetched and moved to HDFS. So Scoop will do automatically for you. You don't have to write Java code yourself. You simply tell that this is a table and this is the schema, etc. Many built-in connectors are already available. For example, MySQL, Oracle, DB2, all those connectors are available within Scoop. So you don't even have to write anything. What are the use cases or benefits? If you have to you want to do some data imports, move certain data from external stores and your enterprise data warehouses into Hadoop, then Scoop is the best framework to do. Parallel data transfer, as we discussed, it launches MapReduce jobs to pull the data, so it is parallelizing it. Fast data copies, okay, from external systems into Hadoop. Of course it's fast because it's parallel. Then there is efficient data analysis. Okay, improve efficiency of data analysis by combining structured data with unstructured data in a schema or on read data lake. So you moved data from RDBMS or data warehouse into HDFS, plus you have application logs and all those things into HDFS, and you can combine those, do all kind of analytics. So it will be more efficient than just working on logs or just working on flat RDBMS tables. Load balancing, it mitigates excessive storage and processing loads to other systems, because now this scoop layer or extraction layer, if we can call it so, it is a separate layer, right? So you don't have to write customized scripts and deploy it or schedule it on your database servers, etc. So this basically is doing load balancing in the sense that now this layer is totally independent from your database server. So of course, if the scoop script is running and it is pulling data from data warehouse, of course there will be some load on your data warehouse or RDBMS, but at least all those scripts, etc., you don't need to run it on your servers. Okay, so this is how the flow works. We have scoop client where we can use CLIs or browsers. Okay, Scoop server is there. Okay, built-in connectors are available for different RDBMSs. So when this is launched, it will create MapReduce jobs. Okay, for example, we can do in map, we are pulling from multiple sources: RDBMS, data warehouse, document and systems. Then we are doing reduce tasks where we are putting it back to say HDFS and HBase, etc. And finally here analytics will happen, and again from here we can send it back to our RDBMS, etc. This is the end of second presentation of the series, and this covers This completes basically both the sessions. And if you have any discussions, points, comments, please make sure to share those in the comment section, and I will get back to you as soon as possible. Thank you guys very much for your time.